All right. So indeed, so this work is set in the context of constraint satisfaction problems. And our goal is to create explanations of certain inferences that a solver makes by breaking this up in very small pieces that are easy to understand. This is joint work with Thias Kunst, and Emilio is a joint PhD student of us, and Jens Klaas is a former master's student. Since this is a bit of an unconventional setting for conferences, I also decided to order my slides a bit in an unconventional order. So are there any questions? I know that Frans is especially spoiled this morning. He told us I always have this default question: how tailored is this to well, whatever formalism you're using? And so the answer to that is not very tailored. So I said it's in the context of constraint problems, but in fact, first of all, the ideas that I will present, they're applicable to any, say, model search formalism, for instance, answer set programming, for instance. Parts of it are presented in the context of propositional logic, but also our ideas actually show how to construct some kind of a proof. And I think it would be interesting to go deeper into the relation there, to go see to which extent we can well, exploit this and reuse methods that have been researched to construct simple proofs in our setting and the other way around as well. So the conclusion of this talk would be that what I present is a relatively young research project. We started working on this roughly a year ago, and there's lots of open questions still. So we will see some. I will already give partial answers to some of the questions that are raised here. But the overall goal is that we have a constraint solver. It does a lot of reasoning, and we want to explain to a human how the conclusions the solver makes can be made. So what's important is we don't want to explain how the solver obtained that conclusion, but we want to search explicitly for an easy way to obtain the same conclusion. Okay. So what we will try to do that is to explicitly go search for small comprehensible steps in this sequence, which can be seen as steps in the proof or steps in some form of propagation mechanism. We will also see some mechanism to explain these steps at different levels of detail, some form of abstraction, you could say. And these definitions, they will trigger new algorithmic needs. I will present an algorithm that at the moment we wanted to write it, well, there were no tools for certain blocks in it. We're now working on it. Demonstrations will be done on logic grid puzzles. So these are Einstein puzzles or zebra puzzles where you have some clues. We'll see an example of it soon. You have some clues and then you have to figure out which entities belong to which other entities. And some history. We started working on this topic because of the Holy Grail challenge last year. So it was on the workshop of progress towards the Holy Grail. And the challenge there was, well, these logic grid puzzles, they exist. They're often found in puzzle books. And there were three main parts of the challenge. And one was try to parse these puzzles, their natural language clues, and translate them automatically into some form of logic or constraint representation. Challenge 2 was then solve this automatically. And challenge 3 was now explain, actually, I think it was formulated in the challenge, explain in natural language how a human could have solved this puzzle. So we were lucky in the sense that this master student that I mentioned, he had done his master thesis on parsing this type of puzzle specifically. So for us, step 1 was already checked off. We had a tool for that. Step 2 was not so interesting because these puzzles are made to be solved by humans. So for a solver, they're not challenging. So there was not a lot of challenge in there. So once you have a model of this puzzle, it's easy to solve it automatically. And then step 3 was the most challenging one. We decided not to explain the natural language, but instead with a visual interface that I will show later, because the natural language tended to get too convoluted, the sentences started to get too long, and it was not so understandable in our opinion. We didn't do any user experiments, so that's still something that should be done. yeah, and we kept on working on this. We recently presented this at ECAI as well, and an extended version of this paper is now under review, as well as another conference paper in which we focus more on the algorithmic needs. So what we did until now was, first of all, formalizing the stepwise explanation problem. So how to break up what we want to achieve, what are good steps, and so on. Proposing some algorithm for it, as well as some heuristics for guiding the search for these explanations. And we demonstrated this on a puzzle, on these logic grid puzzles. And then some unpublished work that I will also talk about today is the nested explanations, which is explaining things at different levels of detail. I'll also demonstrate it in our visual interface. And then also incremental algorithms for finding unsatisfiable subsets. These algorithms, they come into place to solve the efficiency bottleneck of this generation of these explanations. So just let me sketch the setting in which I will demonstrate everything. These logic grid puzzles. There's a set of clues in natural language. There's a set of entities in these clues, for instance, the Englishman and so on. And these entities need to be linked. There's Englishmen, there are people, there are houses, there are animals, and they have to be linked. You have to figure out who lives in which house and who owns which pet and so on. You know that every entity is linked to exactly one entity of each other type. So every person lives in exactly one house, has exactly one pet, and so on. And these links are consistent. So if the Englishman lives in the red house and the Englishman has a dog, then the dog lives in the red house as well. Okay. And so each entity being linked to exactly one another will be called bijectivity, and the consistency of these links will be called transitivity. So in our demo, what we do there is we automatically generate a constraint representation from natural language. And the reason why this is important is that we don't try to optimize the constraints for the explanation problem. So the constraints we're getting there are from a perspective of modeling this problem to be solved efficiently or to be explained efficiently. They're terrible, but they're automatically generated, and so we didn't touch them in order to create some sort of mechanism that's also works for not so good models, so that we don't assume that these models are created perfectly with the explanation in mind or anything. We also didn't modify any of the underlying solvers, and by that I mean earlier work in the context of constraint programming has explicitly added explanation mechanisms to the propagators, and that can then be used to explain how the solver reasons. But we view the solver more as a kind of a black box that does some derivations, and then we're gonna feed him, say we're gonna extract without touching his inner workings. We're gonna try to extract the core of why something follows. Just to demonstrate these logic grid puzzles, I will show you here. You can play around with this yourself. So we have here on the right side, we have clues, and on the left side, we have a grid that needs to be filled in. And the puzzle you see here, that's what we call a pasta puzzle. It's an interesting one. It was sent to us by someone who thought, well, is this puzzle actually correct? So it's quite a difficult one. It's well, I think the most difficult of this type of puzzles that I've seen. So if you want to try to solve it at some point, have fun. And our explanations are of this form. In the beginning of the puzzle, it's quite simple. There's a clue highlighted. The person who ordered capellini sauce, capellini paid less than the person who chose arrabbiata sauce. So from that, we can conclude, for instance, that arrabbiata sauce didn't have the cheapest cost for. So we can conclude a minus here. And this goes on in the beginning. There's not a lot of interesting stuff going on. There's just a single clue, and from that you can conclude some facts. After a while, it gets more interesting. For instance, here, what you see happening here is that we previously derived that arrabbiata sauce was linked to farfalle. And from that, you can conclude, because of the bijectivity, that arrabbiata sauce was not linked to anything else. That's a bijectivity constraint. Here you see a transitivity constraint. Arrabbiata sauce was linked to farfalle. But arrabbiata sauce was not eaten by Claudia, so we know that Claudia cannot have eaten farfalle. And after a while, these derivations get more complex. For instance, here, this is a pattern that we saw occur quite often. So what you see here is it gives us an explanation, a combination of different of this bijectivity and transitivity constraints. And at first, it's not so easy to see why this derivation holds. But so the explanation here would be that, well, the conclusion is that Damon didn't pay 16 euros for his pasta. But suppose he did. Suppose he did pay 16 euros. Well, which pasta can he have taken? Then he could have taken capellini or tagliolini. These were the only two options for him left. But he paid 16 euros, and 16 was not linked to capellini or tagliolini. So there are no more options for him of pasta to be taken. So that's roughly what's going on here. Okay, so let's make it a bit more formal. So what I assume here is that when I say interpretations, I'm presenting this in the context of propositional logic. So we have some theory T, which is a set of constraints expressed in propositional logic, but you can use another formulas as well. And we have partial interpretations, consistent sets of literals. And we're looking for explanations. Explanations are actually a subset of the theory, a subset of the interpretation we have so far that can derive a new literal. Okay. We're not just interested in any of these explanations, but only in at least, say, non-redundant ones, so for which no smaller. So they were called minimal in the previous talk, for which no smaller explanations exist, so no smaller subsets. And in fact, this minimality in itself is not enough for us, because what we saw is that often you can get a combination of 4 or 5 clues that together is minimal and derives something, but it's completely incomprehensible. So what we did is on top of that, so I'll explain this later. What we did is on top of that, we added a cost function that we assume that it exists, a cost function that quantifies how easy to understand an explanation is. And we did not do any effort to make this cost function match human intuition or something. That's an avenue for future work. We just made one up for the logic grid puzzles, saying, for instance, things like using a single clue is easier than using 2 clues. Using only a bijectivity or only a transitivity is very simple because it's always the same pattern. So we just made up a cost function that our algorithms work with if you would change the cost function, if you would learn it, for instance, from human experiments. And so one core observation is that these non-redundant explanations, there's a nice one-to-one correspondence between unsatisfiable cores and non-redundant explanations. So if you want to explain something, we can also ask for an unsatisfiable core by adding the negation of the thing to explain. And that's what we will use in our algorithms. So we added this cost function. And our goal in the end is to compute a sequence of simple explanation steps such that a certain interpretation is reached that we wanted to explain. In the context of these logic grid puzzles, it's a unique solution that we want to reach. So actually, conceptually, you can get it by propagation if your solver is smart enough. So that's the interpretation we want to reach. And we somehow want to minimize some aggregate over the sequence. So maybe what we worked on mostly is we wanted to minimize the hardest explanation step because that allowed us to do a greedy algorithm. But in principle, the cost of this entire explanation could also be, well, you could play around with it and use different cost measures there as well. So what we did is, I already spoiled it. We have a greedy algorithm that just what it does is at each step, we aim to find the simplest explanation. And by doing this, what we do is, well, for each literal in the final interpretation, the one we want to reach, we search such a minimal unsatisfiable core, and then we pick the cheapest one of all the ones found. There is some caching going on, it's not important. And it's built on the IDP system. But there are some problems with this algorithm. First of all, actually, I also already mentioned this, that this minimality in itself is not enough. We would actually like to not search for a minimal unsatisfiable core, but one that is optimal with respect to our cost function. But unfortunately, there were no algorithms for that yet. So in the ECI paper, we just worked with the minimal unsatisfiable cores. And because of this lack of optimal unsatisfiable core calls, we had to use some heuristic methods to work around this issue, basically, where we used an approximation of the cost. It got quite complicated. And also because of that, there was no guarantee that we would actually find the easiest next step. And there were a lot of calls to this minimal unsatisfiable core, so it was terribly inefficient. Now, so for the algorithm, the one that we actually wanted to write was this. What we do, and this is for explaining a single step, it would be, well, for each literal that we want in the final interpretation, find an optimal minimal unsatisfiable core or an optimal unsatisfiable subset. But that's, well, of course, it didn't exist yet. So in the EKI paper, it doesn't look like this at all, but that's the core. That's what we actually wanted to do. And well, we visualized this. So for our cost function, I already mentioned some of these things, that using a single implicit axiom, so bijectivity or transitivity is very cheap. Using a constraint plus some implicits maybe is less cheap, and multiple constraints would be very expensive. And something important here to note is that actually using a single constraint only by itself will rarely be possible. The reason is that, as I mentioned before, the encoding that we get, the logical representation is quite bad. So what we would get, for instance, for this clue, the person who ordered capellini is either Damon or Claudia, is a constraint of this form. There is a person who ordered capellini, and that person is Damon or Claudia. But in itself, this doesn't entail that, for instance, well, whoever one of the other persons is didn't order capellini, which is something we could derive from that. So this will always, the phrase, the person who, implicitly has this bijectivity constraint in there, or this uniqueness of the person who ordered capellini, which is not present in the logical representation. So that's why it says here single constraint plus some implicits is, well, less cheap, but it doesn't fall in the very expensive category, because almost all derivations will be of this form. So how could this be used in practice? Well, one use case could be to teach humans how to solve a certain problem. That's how it was originally phrased in this competition. Another use case could be to quantify problem difficulty. We could analyze what's the best explanation we could find for this specific puzzle, say, and based on that we could go quantify how difficult it is. Do you have to use very difficult steps or not? But in a more, or as a help button, it says here, so if you're stuck, help me solve the puzzle. But in a more realistic setting, we see this to be used in interactive configurations or interactive planning, interactive scheduling systems, where there's a domain expert making a schedule, making a plan, making a configuration, and is assisted by some solver that has parts of the scheduling knowledge, and that sometimes tells him, well, if you put that one here, then this follows. Then you have to schedule this other course in this room specifically. If the solver makes this kind of claims, the expert might wonder at a certain point, okay, why? And then it could be explained why a certain derivation was made by the solver. And the next step was that we did was this nested explanations, explaining in different levels of detail. And actually, I already showed this to you. So what I did here when we were at this step, I explained this in some form of a counterfactual way. I said, well, suppose that Damon did pay 16, and then we started reasoning about this. And what we added to our system compared to the EKI paper is a method to do this automatically. So when there's a derivation step, many of them will be clear to a user, but some might not. So like this one, the first time you see it, it might not be clear why this fact is derived here. And that's what the help button is for. And what we do in that case is you can select which derivation you didn't understand, but there's only one here, so this one. And what we will do then is counterfactually assume the opposite. And then only using these things that were highlighted, we will now come to a contradiction. And then you can see, okay, but if Damon would have paid 16, then by transitivity, since he didn't take Farfalle, Farfalle cannot have been costed 16. Same for Rotini. And then here you come to a contradiction. So the mechanism inside here is exactly the same as before. This kind of explanation steps is the same as before. The search for them is the same as before. It's just, so the goal is now to come to a contradiction, and the interpretation we start from now has this wrong fact in there. And we're only allowed to use the things that claims to be used in this high-level explanation step. So this is a form of counterfactual reason or proof by contradiction. And the goal of this is to explain the hardest steps of the sequence in more detail. So another next step that we're working on right now, actually still, is computing its optimal unsatisfiable subsets. So we're working on algorithms to compute them based on the hitting set duality that's often used in MaxSat as well, and also for other algorithms for unsatisfiable subsets. And what we're adding on top of that is, so I think I would say that our algorithm is quite a straightforward extension of an algorithm for cardinality minimal unsatisfiable subsets. Smallestness is the S. But what we're adding on top of that is a form of incrementality, because we know that during such an explanation sequence, there will be many calls to find unsatisfiable subsets. So the question we ask is, how can we optimally reuse knowledge obtained in previous calls? So that's why we developed incremental algorithms. And the second extension is something we call constraint omnibus computation. The idea there is that in a single step, so remember this loop here, we will do for all literals, we will try to find an optimal unsatisfiable subset or an optimal explanation. Our idea was, then, can we not do this at once? Could we not do this at once by throwing all these literals, not just one by one, adding them, but adding all of them together, and then calling an optimal, and then searching an optimal unsatisfiable subset. Now that in itself doesn't work. What you need to do then, conceptually, is you cannot just search if you would at the negation of all literals that you might want to derive. You cannot just search for an unsatisfiable subset, but you need to add some sort of meta-level constraints on which unsatisfiable subsets you're interested in, namely the ones that contain exactly one of those literals. These are the interesting ones. And actually, so we extend our algorithm a bit to allow for this meta-level constraints of which unsatisfiable subsets you're interested in, and that allows you to actually replace this entire loop by a single call to an constraint omnibus, as we call it now, solver. We don't have a lot of experimental results yet. There seems to be this constraintness seems to speed up just by preliminary results, seems to speed up quite a lot because of avoiding this whole loop, but I cannot give you any interesting results there yet. There are some more topics for future work here. One thing is that we might want to learn the optimization function from humans. So for instance, we now just invented a cost function, but human experiments with humans could give us an idea of what a good cost function is, or maybe also the level of detail or the level of abstraction that they want to see something explained in. We might also be able to learn that. We also don't just want to stay with explaining inferences, but explaining different types of Y queries, for instance, contrastive queries as well. And we want to figure out how these steps, splitting this up in small steps, can be useful there as well. We're also still working on scaling this up, so on trying to find more efficient algorithms specifically for this generation of unsatisfiable subsets. Yes, and I already mentioned that the different Y queries, also their incrementality might be, if you know that there will be multiple queries, there might be some dialogue going on, explain this, but if you give me this explanation, I might want to know more about that. Incrementality might become important there as well to be able to do things efficiently. Okay, then I thank you. And if there are any questions, I'd be happy to answer them.